of stationary process. Okay, so before I get into this topic, let us just start this video with a small example. Let us assume that I'm going to place a temperature sensor outside my house in order to determine the temperature which is varying with respect to time. And this temperature sensor is actually going to measure the temperature every minute. Okay, so I'll be having an n number of values for every minute. So I'm just going to pick the first 5 minutes value. So the temperature is 30 degrees Celsius at first minute, 31 degrees Celsius at second minute, 29 degrees Celsius at third minute, 30 degrees Celsius at fourth minute, and 31 degrees Celsius at fifth minute. Okay, we could see that there is no relationship between these values. It is just varying randomly, right? So whenever I have a sequence whose values changes randomly is what I call it as the random process. Okay. Next, we also have a term there which is called as stationary. Generally, we define stationary as something which does not change, right? Which remains constant is what I call it as stationary. But it is not actually the right meaning. So it does not actually denote only a constant value, but it also denotes that whenever the statistical properties remains constant over a time, then I can also call it as stationary, right? For example, if I'm tossing a coin, there is just two things which is going to happen when I toss a coin. Either I get a head or I get a tail. I get it twice or thrice, I can get the head. Twice or thrice, I can get the tail. But you can say there is a possibility of getting only the head or only the tail. While we are discussing about the probability of getting the tail is just 50 percentage, right? And getting tail is just 50 percentage. If I toss the coin today also, there is just 50 percentage of getting the probability of getting head. If I toss the coin tomorrow also, I'll be having only 50 percentage of probability to get the tail, right? So this is what we call it as the stationary process. So the statistic does not change over the time. It is going to remain constant. Today also it is 50%, tomorrow also 50%, day after tomorrow also it is going to be 50%, right? So the statistic remains the same. So this is what we call it as a stationary process. You can also have another example as the noise in a classroom. Okay, so suppose today I'm measuring the noise in a classroom. When the teacher is not available, you're going to be arrogant, right? So that noise is going to be 55 decibel, 58 decibel, 54 decibel, 60 decibels, and 57 decibels. So but the average in a day is 57 decibel, and the variance is going to be 4. And if I measure it tomorrow also, the average is going to remain the same. By this, we can come to a conclusion that whenever the statistic of a process remains the same, then I can call it as a statistic process, or I can also call it as a statistic random process. Okay, but when I'm discussing about the stationary random process, there are generally two different types of stationarity that generally occurs in a signal. One is the strict sense stationary and another one is the wide sense stationary. While I'm discussing about the strict sense stationary, we can say that everything about the probability distribution remains the same. For example, today I'm measuring the pattern of a rainfall. Okay, let the pattern of the rainfall be 2 centimeter, 5 centimeter, 1 centimeter, and 4 centimeter. If I'm measuring the rain tomorrow, which I'm getting, it is 3 centimeter, 6 centimeter, 2 centimeter, 5 centimeter. It is clearly evident that actually the numbers are changing. It is not constant. But the complete probability distribution of this value is actually identical. Okay. So nothing changes statistically. So this is what I call it as the Strickson stationary process. When you think of a strict and stationary process, you can easily say that the mean is going to remain constant or unchanged, the variance is going to be remain unchanged, the probability is going to be remain unchanged, the distribution is going to remain unchanged, and the higher moments also remains unchanged, which means even though the values is changing, but all these values, statistical values, which is the mean, variance, probability, distribution, and also the higher moments will remain the same, then I can say such kind of process as the strict sense stationary process. But while we are discussing about the wide sense stationary process, only three things must remain constant. Okay, first, the mean will remain constant, which we can denote it by an equation as expectation of x of n is equal to m of x. Mean is nothing but the average value, so the average value is going to remain constant. If I take an example that morning I'm going to measure the temperature, and afternoon I'm going to measure the average temperature, and night I'm also going to measure the average temperature. So all these averages is going to be 30 degree, 30 degree, 30 degree, which means the average remains the same. Then I can say such kind of process as the wide sense stationary process. This is just only one condition. So the second condition is that the variance must remain constant. While I'm discussing about the equation which we have in a book, so expectation of x of n minus the mean value the whole square should be equal to sigma square, which means the spread actually remains constant. Imagine you're having a class test and we are having the mark distribution as 48, 50, 52, 49 and 51, and the average is going to be just 50, and the spread is actually small. The value has deviated as just one or two or three values, right? So next week you're also having in another test. So in that test, some are securing 49, some are securing 50, some of them are getting 52, some of them are getting 48, and some of them are getting 51. And still the average is 50 and the spread is actually small. By this, I can say that the spread is nothing but the variance. The variance in the mark is actually very small. Okay. And the third condition is that autocorrelation will depend only on the time difference. But autocorrelation is actually a new word. It might be confusing for you, right? Let us actually simply explain it. Okay. Suppose I'm playing a music. Okay. Uh, so I'm going to pass the music today and I'm going to play it tomorrow. Okay, or I'm going to hear the same music tomorrow at a different time. Did the music change? No. Previous day, if I hear a word and in the music or a song at the minute 1, if I hear it tomorrow also, even after a time delay of 1 day, in the first minute I'll get the word and in the next day also. This is what we call it as the autocorrelation. We are going to define how similar the two signals is going to be even after some delay is what I call it as the autocorrelation. Since I'm going to measure the similarity between two same signal, that is what we call it as the autocorrelation. Okay. If both the sounds or music is similar, then the autocorrelation will be high. So we can denote it as Rx of L comma K is equal to R suffix X of L minus K. Okay. So here, even though I'm measuring the signal after a time delay at 5th minute and 10th minute, I'm just going to take only the difference between the two different time period, which is 10 minus 5 is going to be 5. Even after I'm going to compare it between a time period of 2 p.m. and 4 p.m., I'm just going to define only the difference in the time, which is 2 hours, not actually merely the sound at 2 p.m. and 4 p.m. Okay. Next is covariance. So covariance is, by the name itself you can say, co and variance. How the two different signals or the two signals is going to vary with respect to time in a similar way, that is what we call it as the covariance, and we can denote it as kx of L comma K, that is equal to kx of L minus K. Here also I'm going to take only the difference between the time period, not actually the two different times. Okay. Next one is the cross correlation. So cross correlation, in the sense, I can say it as, in case of autocorrelation, we have defined it as between two similar signals, right? But if I want to define the similarity or a variation of a signal, two different signal with respect to time, I can go with the cross correlation. Just imagine that you're having a summer season, right? It will be high, there will be high temperature. So because of high temperature, I'm going to use the AC. Because of using the AC, I'll be having an electricity bill. So here I have two different variable. One is the temperature which is caused by the sun, and another one is the electricity bill which is caused due to the high temperature. So I'm going to define how well these two signal characteristics are similar. In that case, I can go with the cross correlation, and it is generally determined by r xy of l comma k, that is equal to r suffix xy of l minus k. Again, here we are going to define only the time gap actually matters, not the actual time. So why do we actually use these type of signals or use these type of random processes? That it is mainly used in mobile communication in order to define how well the signals are transmitting. What is the similarity between the two signals which I have received? Do I have to combine these signals or separate these signals? And it is generally used in radar, Wi-Fi, satellite applications, and in noise filters. In an easier way, in case of the examination perspective, we can say that in case of Strickson stationary process and Whiteson stationary process, the mean is going to remain constant, the variance is going to remain constant, the autocorrelation will depend only on the time lag, and in case of the Strickson stationary process, the entire probability is going to remain constant, but in case of the Whiteson stationary process, it is not the same. And that's all about this video. Thank you.